Okay, so, we are looking at representation and we had stated while we were looking at reasoning is that very often we work with ad hoc predicate names, and we will see as we go along that if you really want to represent really complex things, then you have to be a little bit more careful than choosing ad hoc predicate names. But let us stick with this ad hoc predicate names today and try to see what are the kind of things that we can represent essentially. So, we had said that unary predicates represent categories, that is one of the things we said. And we also said that they also represent properties. So, categories for example, man or ball and so on, and properties like for example, red or mortal and so on essentially. Everything we said we will represent using unary predicates. So, let us see that even if we do that, what are the kind of things that we can express essentially. So, there is the idea in FOL that we have some things are stated explicitly, so a knowledge base for example may be explicit, it is a collection of statements that you are making, but there may be implicit. Implicit could be categories or relations and so on essentially. So, the whole idea here is that what you have in the knowledge base is an explicit statement of facts, but once you know those facts, there are certain other statements which can be implicit, and we can do what Charniak and McDermott call as deductive retrieval. So, to go back to the standard example that we have been looking at, that if the knowledge base has this man, Socrates, and for all x man x implies mortal x, we can ask a query, is mortal Socrates. But to retrieve the answer to that, we may need to do some deduction on the way, and that is why it is called deductive retrieval. So, we may need to apply modus ponens and say that okay, since all men are mortal and Socrates is a man, yes, Socrates is mortal. So, this is an implicit fact, it is not stated explicitly. All that is stated explicitly is that Socrates is a man and all men are mortal, and we want to essentially build systems which allow you to do deductive retrieval essentially. As we will see, this can also ask us, allow us to ask a query like this, that is there someone who is mortal in the system. But keeping in mind that predicates represent either categories or properties, for example, if they are unary in nature, or if they are binary, they express relations between categories. So, what are the kind of things that we can define explicitly and what can we define implicitly? So, we can talk about what we sometimes call as terminological facts. How can we define a set of categories and how can we define more categories in terms of those categories essentially. So, let us say that we have these things explicit. So, in some sense I am giving you the schemas for all the predicates. So, we have a schema which says man. So, in the style of databases we will use the term man inside. So, it takes one argument and the schema name is man. So, the meaning is, so since these are ad hoc predicates, it basically is meaning as we understand amongst ourselves. So, this is something also you must always keep in mind essentially. Whenever we use names like man, mortal, so on and so forth, they make sense to us because they have an English meaning that we associate with it. But in the language that we are representing, it is just a subset essentially, it is just a category. It does not have any other connotations about man. So, if you say Socrates is a man, it does not mean that the system knows in some sense that Socrates has got 2 eyes and Socrates has got 2 legs and that kind of stuff, nothing. All you know is that it is a subset of the domain essentially. But anyway, given a set of explicit sets like this, let us say man, woman and let us say parent, so we have a kind of a database in which we know who is a man or who is a male and who is a female and who is a parent of who, and maybe one more fact which is married. So, spouse 1 and spouse 2. We have this in a knowledge base or databases. So, or a set, these are a set of statements. So, you know about some let us say 100 people or something, on all of them what is the, in terms of these 4 relations, which of them is male, which of them is female, who is the parent of who and who is married to who. Supposing you know all this stuff, we can now talk about implicit statements. So, we can for example define the notion of a mother. How do we do that? So, we want to be able to say what is the meaning of mother. So, we can say something like this: for all x, for all y, mother x y is equivalent to saying that parent x y, because the mother is also a parent, and woman x. So, given the explicit predicates man, woman, parent, married, we can introduce a new predicate called mother, and maybe the language that we are talking about says that okay, Yashoda was Ram's mother and so on and so forth. If you want to listen to such stories, we should be able to make sense of what do you mean by mother, and here is a way of defining what this thing. You can even define a category called mother. So, obviously, if you look at the set of human beings for example, then there are some of them which are mothers. So, how do we define them? Any suggestions? I think. So, I want to say for all x, x is a mother is equivalent to saying that within the scope of the universal quantifier, remember there exists a y such that mother x y. So, we can say that somebody is a mother if she is the mother of someone essentially, and we are overloading the predicate name, but we assume that that is only for our benefit, but as far as the system is concerned, you can distinguish it by the fact that one of them has arity 1 and one of them has arity 2, right. So, this is arity 1 and this one has arity 2. So, they are really different relations in the domain. We are just happen to be calling both of them as mother essentially. So, once you have defined mother, we can define other things. We can define for all x, for all y, grandmother. We can define the notion of a grandmother. How do we do that? A grandmother is a mother of a parent essentially. If we can remember that, then we can simply write that. So, there must be of course, a third person involved now. We are talking about the relation between two people x and y, but there must be a third person who stands between them in some sense. So, we want to say that there exists a z such that mother, we can reuse mother now that we have defined it, x z, and we do not know whether that z is a boy or a girl or a man or a woman. So, we use parent z y. So, we can define new categories. So, as an exercise, you can say define what else do we have, brother, sister, uncle, aunt, grandparent, cousin, niece, and so on. Whatever relations you can think of, you can define them. So, the important point here is that our knowledge base or database need not store who is whose brother and who is whose sister and so on. Once we define the 4 explicit predicates that we have, if we have data represented in terms of those 4 explicit predicates, we can answer queries about who is whose brother, whose this thing brother and so on. So, if we ask a query as is Suresh the brother of Sheila, then of course, we can do some theorem proving to see whether that statement is true or not, and that will essentially use all these definitions that we are using essentially. What is more interesting is that you can define the notion of ancestor. So, we want to say we want to be able to define ancestor. Now, defining mother for example, or grandmother or even great grandmother for example, is a straightforward process, because we know exactly how many people are in between, that between a person and his grandmother there is one parent sitting, or between a person and the great grandmother there is a parent and a grandmother or grandfather sitting. But when you want to define ancestors, which is kind of a little bit more vague, how can we do that? And it can be done. So, I want to say so you must think recursion here. We can use recursion, and whenever we talk about recursion, we talk about a base clause and this thing. Right? So, we can say first thing is that our notion of ancestor says that if x is a ancestor of y, it could be that x is a parent of y essentially. So, a parent is also an ancestor, it is an immediate ancestor. So, but it is an ancestor, but of course, what about other ancestors? There we can say, so of course, we must use for all x, for all y and everything there, right. But otherwise, how do we define an ancestor? We can say that ancestor x y is equivalent to saying, now think of the definition of grandmother. and we can use something similar. We can say that there exists a Z, and there are various choices here, and at some later point we will consider which choice is a better choice in terms of efficiency, but at the moment we are not really bothered about that. So, we are saying that okay, x is an ancestor of y if there is a z such that z x is a parent of z and z is the ancestor of y. So, that is the other possible definition essentially. So, either you are an immediate parent, which of course is available in the database, or you can use this second equation or second logical equation to say that okay, you must be having a child who is an ancestor of if x is an ancestor of y, if x is a child y z, and z is the ancestor of y essentially. So, eventually this will work essentially. And how do we combine this in terms of logic? We simply put a disjunction between them and then close the whole thing essentially. So, for all x for all y, either ancestor x y is equal to parent x y, well equal is not the right thing, it is equivalent to parent x y, or ancestor x y is equivalent to saying that there is a child whose parent you are and who is an ancestor of x y. And as an exercise you should be able to see that just create a small database of a few people and you will be able to answer this query using these inequalities. Remember that these inequalities are not inequalities, these equivalences are basically two-way implications. So, whenever I write this is equal to writing this and this essentially. So, I can write a statement like this and a statement like this. So, an equivalence A equivalence to B is equal to saying A implies B and B implies A essentially. So, you can really break it up into implications and then you can use your modus ponens and forward chaining or whatever algorithm that you are using essentially. So, let us, since we are computer science students, let us take a small exercise and try to define a connected graph. We want to be able to say that a graph is connected. So, I will just outline the process here and I will leave it as a small exercise for you to do. So, now if you remember that what is a graph is basically a collection of nodes and edges, right, and nodes is basically a set n1 n2 n k and edges is another set which is of the form, for example, if I say E I j, then remember these are all terms in a language. So, they denote objects in the domain. So, E I j I could say is equivalent to saying that there is a function called edge between n I and n j. So, an edge is basically a pair or a pair of nodes, or you can explicitly call it an edge and then so on and so forth. And a graph is a term which will stand for a set which is defined over a set of nodes n comma e. Remember all these are terms essentially, including a graph is a term, it is an object in the domain essentially. And what we want to define is something called connected. We want to define a predicate called connected. We want to be able to say that the graph is connected essentially. How do we do that? Any suggestions? We can replace this definition of connected by saying there is a path between every pair of nodes. So, you can see that this part, every pair of nodes, now you can say for all n 1 comma n 2. This is also a notation for saying for all n 1 for all n 2 essentially, that for every node, which are these nodes? For these nodes must belong to the such that n 1 belongs to n and n 2 belongs to n. Remember, n is a set of nodes that we have. I have written belongs, so you could have chosen a more logical looking predicate, let us say belongs n 1 comma n, but it is the same thing, since we are more comfortable with this. So, for all this we want to say that there is a path n 1 n 2. Any idea of how to? Now, we need to define the predicate path. Any suggestions on how can I define that there is a path from node n 1 to n 2? So, essentially when I said define, I mean I am expressing a logical statement which will be true whenever there is a path from node n 1. So, I say path n 1 n 2 means in the domain, in the graph, which is a collection of nodes and edges, if I were to start from n 1, I will find a path to n 2, which means I will find a sequence of edges which will go to n 2. So, any suggestions of how?
There is a edge from n1 to some vertex, and from that vertex there is a path to n.
Okay, good. So, that is like defining the ancestor, right. Just as we define ancestor, we can define the path essentially. We can say that you have a path from n 1 to n 2 if there is an edge between n 1 and n 2, and the other clause, recursive clause would be that there is a path between n 1 and n 2 if there is a third node n 3, such that there is a node between n 1 and n 3, and there is a path between n 3 and n 2 essentially, which is analogous to this notion of defining ancestors essentially. Then we can define other kinds of properties. So, we are talking about terminological facts. We can define more properties about the domain, and these examples that I am taking are from the book Brackman and Levesque, which is one of the textbooks that we are following for this course. So, you can say for example, disjointness. So, you can say for all x man x implies, in other words, we are saying that the set of men and women is disjoint. We can talk about subtypes. So, we can say for all x surgeon x implies doctor x, that a surgeon is a subtype of a doctor. And a little bit later in the course we will have a lot more to say about this, because when we talk about ontologies and description logics, they are essentially talking about this kind of relation. One of the very important relations is a subtype relation essentially, or subsumes relation. The set of doctors contains the set of surgeons and so on and so forth, but we can express this in first order logic by a simple statement which says that all surgeons are doctors essentially. Then we can say that our definition is exhaustive. We can say that for all x, if one is an adult, implies you must be either a man or a woman. Then we can talk of symmetry. We can make statements like so, notice that all this is trying to create a knowledge base in which the explicit facts will be minimal, whereas the inferred or the implied facts will be a lot essentially. So, whenever you say that Suresh is married to Sheila, it is equivalent to, you can say that also that Sheila is married to Suresh, but since we are dealing here with all syntactic entities, we have to do this explicitly. I mean, for us it may be like something which is obvious, but not for a logic machine. And we can have inverses for all x, for all y. Then we can restrict type. Type is another word we use for category, for example. So, we could say for example, that if two people are married, then they must be humans, let us say, or persons. So, in some sense we are saying that only people can be married essentially. Okay. Then we can have compound definitions. So, we can say for example, for all x, rich man x implies rich x and man x. In fact, we can use a equivalence sign here. So, we can define compound predicates like rich man, democratic country, and so on and so forth essentially by combining predicates in this manner essentially. Again we will look at that more when we look at description logics essentially. So, this gives us a flavor of how do we express relations and define new relations in terms of old, even when we are using ad hoc predicates, but we will see as you go along that ad hoc predicates is not a very good idea, because the number of predicates you may have to end up creating is far too many essentially. So, you need some degree of economy there, we will come to that later. But meanwhile, in the next class we will look at the notion of properties, and we have not seen how properties will be represented. So, for example, I will leave you with this question as to how do I express the fact that the ball is red essentially, and we will take it up in the next class.